Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is Lecture 2B, Part 5. This is the last video in this section for using the limiting distributions, or finding limiting distributions using moment generating functions. We're going to call this video 5B. And in the last video, we went over the proof of the central limit theorem. And we're going to use some of the techniques from that in the examples for this section. So it's very important that you understood the proof of the central limit theorem. If not, you need to go back and review it. Otherwise, the examples today may not, or in this video, may not make that much sense to you. So I hope you enjoy the video, and so let's get started. Now let's do an example using the results and some of the techniques we found last time in the proof of the central limit theorem. Okay, so we're going to let x1, x2 up to xn be a random sample from an exponential distribution where theta is equal to 2. Okay, so we have that x is an exponential 2 here. We want to find the mgf of w equals x bar minus theta over theta divided by the square root of n. Now, remember that e of x is equal to theta, and the variance of x is equal to theta squared. So the mean and the standard deviation are the same, which is theta, and that's what we're seeing here. Okay? Now, notice that this is an exponential, so for xi, okay, so this is x bar. So for xi, the mgf xi is going to be equal to 1 over 1 minus 2t, and t has to be less than a half. This is the mgf for a gamma distribution, specifically the exponential. Okay, so here you have to know your mgfs, or this is going to be a long and difficult problem. So we want e of e to the tw, which is equal to, we know, m of t over square root of n, all raised to the nth power, where m of t is equal to e of e to the t times xi minus mu over sigma. We just made a substitution for w without the n, all right? So for each xi, so we haven't added up or multiplied to get the n involved yet. Okay, so this is for each random variable, and we have negative h t over square root of n h, and this is by 6 above. So back during our proof of the central limit theorem, there's number 7, and where did 6 go? I missed it, didn't I? Yeah, 6 is over here. There we go. So this is what we're using. So this, I've put a number by this because it's important for you to know it. And 7, I put a number by it because we needed it for the proof. And so 8 is here, and we needed it for the proof. So 6 is one that you're going to use. So you might want to make sure that you put it on your formula sheet. Okay, so where m is this, and now we see that m of t is equal to the expected value of e to the t xi minus mu over sigma, which is equal to the expected value of e to the t xi minus 2 over 2. We substitute in for mu and sigma here, okay? And because mu equals theta and sigma equals theta, okay? And theta equals 2. Oh, that's kind of sloppy theta. Got to be careful with that. Don't want it to look like a sigma. All right, so that's how we did that. And this is equal to e of e to the t over 2 xi minus t. Okay, so 2 over 2 is 1, right? So we distributed that, or expanded it, we should say. Distributed the t across the across this quantity here. Okay. Now this is equal to the expected value of e to the, now I can just break this up as a product. So e to the t over 2 times xi, and then e to the negative t. Now, e to the negative t, if we're doing this with respect to x, okay, so this expectation is with respect to x, our random variable, and so t is a constant in this case, so we can pull it out of the, I don't need to do that, of the expectation. So this is going to be e to the t over 2 xi, okay? And then this is equal to e to the negative t times m of xi, t over 2. So this, now I plug in, so e to the negative t, I use the mgf, so it's going to be 1 minus 2. Instead of t, we're going to put in t over 2, which is equal to e to the negative t over 1 minus t, and we know that t has to be less than 1 in this case, okay? So using again our what we know about, instead of t is 1/2 or t is less than 1/2, here we have a 1, so it's t is less than 1. Okay. Then m of w of t is equal to e of e to the tw, which is equal to m of t over the square root of n, that quantity raised to the n, and now we substitute n, so we have, now remember we have to substitute in t over the square root of n into what we had up here. And so we end up with e to the negative t over the square root of n divided by 1 minus t over the square root of n, quantity to the nth power, okay? Because we have to raise it to the nth power then, which we can write as e to the negative t over the square root of n raised to the nth power, so we'll multiply exponents there, and then 1 minus t over square root of n to the nth power, and we can simplify this as e to the negative t times square root of n by multiplying the exponents over 1 minus t over square root of n, quantity raised to the nth power, where t is now less than the square root of n. Okay? 1 over, remember? 1 over, we use 1 over whatever is multiplied by this t here for the gamma distribution. Okay, so there we go. Now, we want to use the mgf, so we figured out what the limiting distribution of this is. And so we have a gamma distribution now for the limiting distribution. And we use the mgf of w, and we compare it to m sub z. This is a standard normal distribution. So the z is a standard normal distribution. So we compare it to the mgf of z. So we're using n equals 5, 15, and 50. And this is from your book. Well, it turns out that the exponential 2 is also the chi-squared 2. So it's important to know that as well. So we have n equals 5 is this first line, 15 is the second line, and 50 is this line. And then this other line is, this last line over here is the standard normal. And so you can see as n increases, this approaches the standard normal, which is exactly what we expect from the central limit theorem. So we're going to use a U-shaped distribution, and we're going to call that random variable x, and it's distributed as f of x equal to 3/2 x squared. X is between -1 and 1. And then we want to show that m sub w of n, the moment generating function of w sub n, approaches m of z, the standard normal, as n increases towards infinity. We're going to use sample sizes of 2, 5, and 10. So this actually does this pretty quickly. We want to first find the moment generating function of x, then the moment generating function of w sub n, and where w sub n is given here as our standardized variable, and then we're going to graph the moment generating function of w sub n for the different, for the values. Oops, I can't seem to write values. Values of n equals 2, 5, and 10. Okay, so let's get started. So I here is, we want to find m moment generating function of x of t. Okay, and so this is going to be e of e to the tx, and we could say xi if we want here, so that we're consistent with the last time. So this is a continuous function, so now we're going to, we don't have the information for a U-shaped distribution. We're going to have to calculate it. So this is going to be e to the txi, I'll say, f of x xi dxi. Okay? Well, we've only defined x. X is only the support, I should say. The positive values of f only occur when x is between -1 and +1, so we can replace our limits of integration with -1 and +1, e to the txi, and then f of xi is going to be 3/2 xi and then dxi, which can be rewritten or combined as 3/2 xi squared e to the txi dxi. Okay. Now we're going to have to use integration by parts here to get this. So let u equals 3/2 xi squared, and let dv equal e to the txi dxi. And then we have that du is equal to 3 xi dxi, and v has to be the integral of this, so this is going to be 1 over t e to the txi. Okay? And so this means that the moment generating function of xi is equal to 3/2 xi squared times 1 over t e to the txi, and that is from -1 to 1. And I'm going to write that, I'm going to be specific here so I don't forget that I'm using x instead of t. xi is equal to -1, from -1 to 1. And then we subtract the integral from -1 to 1 of, so we're going to put, so this first, remember this is u times v, and then minus v du, minus the integral of v du. And this was the integral of u dv. So, or I should put it down here, the integral of u dv is equal to that by integration of parts. Okay? So that's what we're doing here. We're going to put v times du, and that's going to give us 3 over 3xi over t times e to the txi dxi. Okay? So now we have that m of xi of t is equal to, now we're going to evaluate this first term here. Maybe I'll change the color here. So the first term here has to be evaluated, and so we're going to plug in 1 and then subtract, plugging in -1 for xi. And so here we get 3 over 2t, and then we'll have 1 squared, so that's just going to be 1, e to the t times 1, a negative. Do we have a negative up there? We don't have an, oh no, we have a t. Okay, so for +1, we just have a t. Okay, so we have, this becomes 3 over 2t e to the t, and then for the -1 for xi, we're going to end up with 3 over 2t e to the -t, and then we're still subtracting this integral from -1 to 1 of 3 over t xi e to the t xi dxi. Now we have to do integration by parts again. So now we're going to let u equal 3 over t xi, and dv will equal e to the t xi dxi. And so du is going to be 3 over t dxi. V is going to be 1 over t e to the t xi. We're taking the integral there. And so again, this is going to equal, we've got the first two terms, don't forget these, and then this goes with the integral here. So this is 3 over 2t e to the t minus 3 over 2t. So I could combine that and make this a little easier to write, since and so this would be 3 over 2t e to the t minus e to the -t. So that's a little more compact. And so we have u times v, and that's going to be 3 over t squared times xi, and this is going to go from xi equals -1 to 1. Whoops, doesn't look like a 1. And then minus, now we already have a minus out here, that's why this is a minus here. And so if we subtract and we have a minus, we're going to end up with a plus. And so we end up with, let's see, we have minus the uv, so plus, so it's going to be minus uv, and that's what we have here. And then we have a plus, and we take the integral of v du, and that's going to be from -1 to 1, 3 over t squared e to the t xi dxi, I believe. 3 over t squared e to the tx dxi. Yep. And then this is going to equal 3 over 2t e to the t minus e to the -t. And then we have minus at 1, that's xi equals 1, that's going to be 3 over t squared. And then it's going to be, for xi equals -1, we're going to subtract, that's going to be a positive. And again, 3 over t squared. And, and I forgot the e here, so I need to come back here and put in the e to the t, because I left that off, and so this needs to be a little different. So this is going to be minus 3xi over t squared e to the txi, and that's from xi equals -1 to 1. And so now when I evaluate that, I'm going to plug in the +1 and then the -1. So the +1 is going to give me there supposed to be an xi? No, there's not, is there? No, there's not supposed to be an x there. So this is going to be 3 over 2t. Oh, yes, there is. I'm sorry. This is u times v. That's these two. So there is an xi there. So there we go. So now, when we plug in a positive, we have a, for xi, we have a 3 times a positive. So we have a 3 over t squared. And then we have e to the t. And then we'll end up with a positive. When we plug in a negative, that'll change this sign here. So we end up with a positive 3 over t squared e to the negative t, though. And so, so we have a negative, but we're subtracting. So, okay, so we end up, so we're subtracting this one, and then we have a negative. So we already have a negative, we subtract to make it positive, and then we multiply by a -1 to make it negative again. So this sign is going to be a negative, so be very careful with that. You might want to use parentheses. That's what I did originally. I put this, and then I had a minus, and then I had a, so this became a plus inside the bracket, okay? But I still have to distribute it, so. And then I take the integral of this term, and that's going to be 3 over t cubed. So this is going to be plus 3 over t cubed e to the txi from -1 to 1. And so this is going to be 3 over 2t e to the t minus e to the negative t minus, I can pull out a 3t squared there, so I've got 3 over t squared e to the t plus e to the negative t. It's going to be a plus, a negative plus, yeah. So negative. Okay, so if I pull out the negative, then that's going to be a plus, right? Okay. And then I have plus 3 over t cubed e to the t minus 3 over t cubed e to the negative t. Okay. So now I should end up with, I'm going to write this all out individually, 3 over 2t e to the t minus 3 over 2t e to the negative t minus 3 over t squared e to the t minus 3 over t squared e to the negative t plus 3 over t cubed e to the t minus 3 over t cubed e to the negative t. All right. So we can use a common denominator here. We're going to find the common denominator which is 2t cubed. And so we have to multiply this term by t squared, top and bottom, t squared over t squared, so for these two. And for these two, we'll multiply by t over t, and these two, here, the middle two, we're going to have to multiply by 2t over 2t, and these we're just going to have to multiply by 2 over 2 to get a 2 cubed on the bottom. Okay. So we're going to do that, and that becomes 3t squared over 2t cubed e to the t minus 3t squared over 2t cubed e to the negative t minus 3 let's see, this will be 6. So this is going to be 6 over 2t cubed minus 6 over 2t, oh wait, I need to put the e in there. So e to the t minus 6 over 2t cubed e to the negative t plus 6 over 2t cubed e to the t minus 6 over 2t cubed e to the negative t, which is equal to, we have 2t cubed on the bottom, so we have 3t squared e to the t minus 3t squared e to the negative t minus 6e to the t minus 6e to the negative t plus 6e to the t minus 6e to the negative t. Okay? And t is not equal to 0. That's the only place where this is not defined. Okay, so this is our MGF of xi. Okay? So now we want to find B, we want to find the MGF of Wn, and so we want M of Wn of t. And remember, so let's look at what, we need to find the mean and the variance of this. And so to find the mean of this U distribution, so we have to have E of x is going to be 3/2, so x f of x, so this is going to be cubed dx from -1 to 1, and this is going to be, so x to the 4th divided by 4, 3/8. Okay, so we have 3/8 x to the 4th from 1 to -1. And this is going to be 3/8 minus 3/8 equals 0. Okay? Now it's a U-shaped distribution. If you know that it's a U-shaped distribution, and you'll know that the center of the range is going to be the mean, and at x equals 0, this is 0, so we could have figured it out that way. We also need the variance of this, and I'm sorry we don't have much room, but I'm going to do ex squared is equal to the integral of 3/2, so x squared f of x, that's going to be x to the 4th dx, which is going to give me 3/10 x to the 5th from -1 to 1, which is going to give me 3/10 minus a negative 3/10, which is 6/10, which is 3/5. And yes, okay, so that is the variance. So that is also the variance, because the variance is equal to ex squared minus mu squared equals ex squared minus 0 squared. So in this case, it's ex squared is the variance. So now I'm gonna look at w. W of n is equal to, and we have x bar minus mu over sigma over the square root of n, so that's x bar minus 0 over the square root of 3/5 divided by the square root of n, which can be rewritten as x bar over the square root of 3 over 5n, or we can switch this up and square root of 5n times x bar over the square root of 3. Okay? Now, we can write this out as we have the square root of 5n over the square root of 3 times x1 plus plus xn over n. Okay? So this is w sub n. Now we need the moment generating function of w sub n, And remember that that is e of e to the t w sub n. And that is e to the e to t and w. We're going to write it out. And so I'm going to distribute this, and I'm going to write it as 5n over 3, square root of 5n over 3. 5n over 3, okay? I'm going to distribute this across each of these terms. And notice that I have an n down here. That's the same thing as square root of n squared, right? So I'm going to end up with the square root of 5 over 3n here. Okay? Just to make this a little shorter in the writing. Okay, so this is going to equal e to the t, and then I'm going to have the square root of 5 over 3n x1. Do I need to leave it that way? No, I don't. Plus the square root of 5 over 3n x2 plus, all the way up to the square root of 5 over 3n times xn. Okay. All right. And so this can be rewritten as a product. So this is going to be e of e to the t square root of 5 over 3n x1 times e to the t square root of 5 over 3n x2 e to the t square root of 5 over 3n xn. And by the independence, we can rewrite this as e of e to the t square root of 5 over 3n x1 times e of e to the t square root of 5 over 3n x2 e, oh, wrong e, expected value of e to the t square root of 5 over 3n xn by independence. Okay? And this is equal to m of t square root of 5 over 3n raised to the nth power by identically distributed. Okay, because they're identically distributed. And so this is going to be, okay, so we've got t, so we need to put m into this, and so for everywhere that we have, so we need to raise this to the nth power, okay? And we have, okay, so this is going to be 3 over 2t. So we're going to substitute in for, this is m up here. And we're going to raise this to the nth power, okay? Okay. So let me make sure that I'm not, okay, so I've got 3 over, so over 2t cubed, and then we'll have all of that. Yep, okay, so this is equal to 3 over 2t cubed, and then I can have t squared e to the t minus t squared e to the negative t minus 2t e to the t minus 2t e to the negative t plus 2 e to the t minus 2 e to the negative t at t at raised to the nth power at t equals t square root of 5 3n. Okay? All right. So then this can be written as 3 over 2t cubed times t squared minus 2t plus 2 e to the t, and then minus, I need to put my bracket here. I'm factoring out and simplifying. So minus t squared plus 2t plus 2 times e to the negative t, and t is equal to t square root of 5 over 3n, and this is all raised to the, this is all raised to the nth power. And so this can be simplified as we're just factoring out, so this is n. I can write this as 3 over t squared plus 2t plus 2 over 2t cubed, and then e to the t minus e to the negative t to the n, where t is equal to, got the wrong spot there, t is equal to t square root of 5 over 3n. All right. And then we're going to substitute n for this, and we end up with 3 times 5t squared over 3n plus 2t square root of 5 over square root of 3. Did I miss a square root? Yeah, I think that's supposed to be square root of 3n. 3n. And then we have plus 2 over 2t cubed square root of 5 cubed over 3 cubed n cubed, and then all of this times e to the t square root of 5 over 3n minus e to the negative t square root of 5 over 3n. This whole thing raised to the nth power. Okay. And where t just is not equal to 0. Now we're going to look at the graphs of the U-shaped, and what's happening here is this first line is the normal, standard normal, and the furthest line out is n equals 2 for the U-shaped. And so as n goes from 2 to 5 to 10, you'll see that it gets really close to this and converges pretty quickly, and much more quickly than when we did the exponential 2, which is also the chi-squared 2. Okay? So that is it for this section. I hope that I know this has been a long video, but I hope that this has helped you see how to use that proof of the central limit theorem to actually do a problem. And you can see how these different distributions converge in distribution to the standard normal distribution as n increases. Some very quickly, some not as quickly. Okay, so that's all for this video. If it's applicable, make sure that you update your formula sheet or your list of definitions, your list of distributions. But as always, if you have questions, please come to virtual office hours. I'm happy to help you. If you can't wait, if you need help before then by all means email me and I will get back to you as soon as possible. Until then, please take care of yourself and we'll see you next time.